This video is all about comparative analysis of Hexen-Willian equation results versus Pyflow expert results on Shashemenon book example problem 3.5. So now we're going to use already in this book the Hexen-Willian equation result has been solved. Now we're going to use Pyflow expert to compare the two results. That is what we're doing. Now, this is a question. They say a 3-inch internal diameter smooth pipeline is used to pump 100 gallon per minute of water using the Hexen-Williams equation. Now, they say calculate the head loss in 3,000 feet of this pipe, assuming a C factor of 140. So we're assuming a C factor of 140. So that is it. So now let's go to pipe flow expert. So now we're going to make use of pipe flow expert to solve this. Now this problem I will assume is a water, the fluid is water. So now we are going to change the fluid here. Okay, we're going to use the fluid at 50° Fahrenheit. We're going to use this fluid at 50° Fahrenheit. So that is the fluid we're going to use. We'll be using now. We save that. Then next, what we're going to do next is we add pipe. We add pipe from here. Now I will right click. Now I needed to add demand inflow. That is the flow, the flow, a kind of demand inflow. That is, I'm going to put in an inflow into the pipe. So what they call it here is demand or inflow. So now when you check the problem, they gave us 100 gallons per minute. So now we'll just type in 100 gallons, 100 gallons per minute. So now we'll just say, oh, click OK. If I click OK, so this is the 100 gallon in US unit. So now I will now add a pipe from here to here. Now they said I should change the default value, so I needed to change the default value. The size of the pipe material, they say is a smooth pipe. It's a smooth pipe. The smooth pipe, so I needed to add a material that is smooth. So now let me call this, the material that is always smooth is, let's say, PVC. The PVC has a very low roughness, so there is no, now the internal roughness should be 0.000. So this, because they said the pipe is smooth, so now I'll just say save. Cannot be blank. Okay, 0. Let me say 001. So since it's smooth pipe, you just roughly zeros. Okay, now just enter. Now there is no size here, so now I'll add a new size. They said the internal diameter is 3 inches, so I will use a 3-inch pipe. You know, normally the outer diameter of a 3-inch pipe is 3.5. Now if it's 3.5, then I will now make the wall thickness to be 0.250, meaning here will now be 3 inches. look at it thoroughly, it's now 3 inches. Then now I will use mm, I will use the size. This the weight. PVT pipe is very light, so I will just use a size of 1.458. I'll click add new items. So yes, so this is it now. I will now select it and click this transfer selected size. I'll click this transfer selected size, then I'll say save to pipe. So now the whole information is changed now. You see the internal diameter here now is 3 inches. So here the length of pipe is 3000. The length of pipe is 3000 feet. It's 3000 feet. So we are good to go. Now we are good to go. I'll just click OK here. So that is it. Now at the at node 1, this is node 2, and node 1, I'll add a tank there. So this the tank should be empty because so that the fluid coming in will just we now have to fill that empty tank. So we are done. We are done with all that is needed to be added to this. So now I'll just click calculate. So let's look at our result sheet. So the friction loss is 72.95. 72.95. Now let's 72.95. But let me just make a change. We have 72.95. So this is 72.95. So the percentage error will just be bracket open this value minus this divide by this information, okay, divide by what we got for this from the software times 100. So the percentage error is high, is about 9%. Now let's check either the Hexan-Willian equation has introduced a lot of error, because the equation we use to solve this particular problem, the equation this pipe flow expert used, mm, the equation they used is Dazel-Weisbach equation. Now in non-compress this is a non-compressible fluid because it's water. We used water, so this is the only equation for non-compressible fluid. But if it is okay, let's look at this linear. It's just still same one equation. Let's look at now if it is compressible, which is not, you now have, if it is okay, this is not compressible, so but it will not go to that. Now let's leave it back to where it is. But if had it been the fluid is gas, it will activate that. So since it's not gas, it will not activate. So now what I will do now is to change the material. Let's change the material. Now I will use I will use stainless steel, this stainless steel material. Now I will add size 3 inches. So the outside diameter of 3 inches is 3.500. Then I'm using wall thickness of 0.250 to give me 3 inches. Now for steel is of higher, it still has higher weight than that of um, PV, PVC. So I will use 8.428 as the weight. This is an arbitrary value. I didn't get it anywhere. So I will just click add new entry. So these other ones will be calculated based on these values we added here. So that is it. So now select this, click this, now say save. Now we have changed the material. We have changed the material with a roughness, with an internal roughness of 0.002. So let's run and see what the result will be like. So this frictional losses is 82.75. So it's higher now. It's 82.75. Now let me see. Let me see the percentage error. 82.75. While the value for Hexan-Willian equation, the result from Hexan-Willian equation is 79.8. Now let's copy down this formula tool down. So the error here, okay, let me make this an absolute value. An absolute value. Let me make it an absolute value. So let's bring it down so that it won't give us a negative value again. Now, so the percentage error in using a higher using steel. This one I use steel. It gives me a smaller percentage error. Here I use a very smooth pipe. Okay, anyway, smoothness is relative anyway. So now, if you enjoy this video, please hit the notification, hit the subscribe and hit the notification bell, and also do well to share these videos to your friends and well wishers. Thank you.